Hello everyone, I'm Dr. Samidi Navaratna, Senior Lecturer from the Department of Community Medicine. I'll be conducting some of the biostatistics lectures to your batch, and I hope you have a sound knowledge on the descriptive statistics by now. Well, it would have been better if we could have met, in a normal lecture hall setting where we could have done more interactive sessions. But then these are not normal days. So let's do the best. I will try to make it very clear to you as much as possible. But if you have any queries, don't hesitate to contact me. And today's lecture is the first one of a series of lectures, the Inferential Statistics 1. So let's start. In the first couple of slides, I have listed the learning outcomes I expect the student should acquire by the end of this lecture. So the first one is explain the difference between a sample and a population. Second one, explain the difference between a statistic and a parameter. Third one, recognize the symbols used for the mean, variance, standard deviation, correlation coefficient, proportion, and regression coefficient. Then fourth one is provide the definition of sampling distribution. Fifth one, compare and contrast point estimation and interval estimation. Sixth one is explain the steps followed in a hypothesis testing. So the seventh one is construct confidence intervals using sample statistics. Then the last one is interpret statements of probability and confidence intervals. Let's try to understand the difference between the sample and a population. So what is a sample? The sample is a set of cases taken from a larger population. Now consider this as a population. Then sample is a group of people or a set of cases or a number of sampling units that you have chosen out of the entire population. Now, in that case, the population is the complete set of cases, the entire number of sampling units. So, the population is the entire group that you want to draw conclusions about, and a sample is the specific group that you will collect data from. So, remember that. So, let's see. What is a statistic and what is a parameter? So, a statistic is a numerical characteristic of a sample, whereas a parameter is a numerical characteristic of a population. So, in that case, what we calculate is a statistic, whereas the true population value is a parameter. So, most of the time, we can only acquire data from a sample, because either it's too difficult or too expensive to collect data from the whole population, right? So the only instance where we can collect data from the whole population is the census. So while descriptive statistics can only summarize a sample's characteristics, inferential statistics use your sample to make reasonable guesses, inferences about the larger population. With inferential statistics, it's important to use random and unbiased sampling methods if you want to generalize your findings to the total population. Right? So if your sample isn't representative of your population, then you can't make valid statistical inferences. So keep that in mind. So in this slide, I have added an image borrowed from the internet. and it says statistics, the discipline that proves the average human has one testicle. So just for fun, I added it just to emphasize the importance of sampling in your research. So once again, there are two major branches in statistics, descriptive and inferential. So descriptive statistics describe the numerical characteristic of data, whereas inferential statistics make inferences about populations based on sample statistics. So as you all know, with inferential statistics, it's important to use random and unbiased sampling methods for you to generalize your findings to the larger population. Then only you can make valid statistical inferences. This slide summarizes the functions of each branch of statistics. So the descriptive statistics are used to organize, summarize, and present data. So in summarizing the collected data, you can calculate the summary statistics like measures of location, measures of variability, etc. Then inferential statistics are used to predict, estimate, to make hypothesis testing, and then to generalize those findings to a larger population. So in prediction, we use regression models. To estimate, we use point estimates and interval estimates. So we'll be learning about these in this lecture. And then hypothesis testing assess the plausibility of a hypothesis by using sample statistics. And in generalizing, we make conclusions about the population parameters based on the sample estimates. This table gives the symbols used in statistics. Now, as you can see clearly, if you compare the population parameter column and the sample statistic column given here, except for the number or the sample size row, the other symbols used here, the Greek letters are used to symbolize population parameters and English letters are used to symbolize sample statistics. So the mean is represented by Greek letter mu for the population parameter, and where the sample statistic is concerned, the mean is represented by x or x bar rather. So proportion by pi and p respectively, and variance by sigma squared and s squared, and standard deviation by sigma and s. Sometimes SD is used. So correlation rho and r, and regression coefficient beta and simple b. Moving on. So moving on to sampling distribution. What is a sampling distribution? It is the theoretical probability distribution of the values of a statistic that results when all possible random samples of a particular size are drawn from a population. I hope you can understand this word theoretical is very important. So it's not a real distribution. It's a theoretical distribution. Theoretical probability distribution. So how does it work? Now as illustrated here, I have illustrated here, you take all the possible samples, random samples from the population you are interested in, And then for each sample, you calculate a summary statistic. That is, in this case, I have taken the means. So for each of these samples, there's a corresponding mean. Then using these means, you draw a frequency distribution. So then that distribution is known as the sampling distribution of means. Because we have taken means here, you can use the term sampling distribution of means. Of course, you can use other summary statistics like median and standard deviation, etc. too. So, I hope you understood this is not a real distribution, and it is a theoretical one which will assist us to generalize our sample statistics to the larger population. So in this slide, I have put down the steps we followed to draw a sampling distribution, which I have explained to you already in the previous slide, so that you can use this as a future reference. So the important thing in this slide is, please note the last one, the average of all the sample means will equal the true population mean. Okay. So the important thing is, now if you just look at this frequency distribution given here. So if this is drawn using the sample means, then the mean of this will represent the true population mean. The sampling distribution, which we discussed in the previous couple of slides, is governed by the underlying distribution of the population. So if it is a normal distribution, the sampling distribution also will be a normal curve. And it depends on the statistic being considered. Furthermore, it depends on the sampling procedure employed and depends on the sample size used as well. Let's try to understand sampling error and standard error. So, what is sampling error? It's the difference between the value of a sample statistic and the corresponding population parameter. It's rarely that you will get the exact population parameter by studying just one sample. So always there's some error involved. So sampling error is the difference between that value, the calculated value, and the corresponding population parameter. So statistics from random samples vary because of chance. So what is standard error then? Standard error is the standard deviation of a sampling distribution. So we have already discussed about the sampling distribution. So the standard deviation of a sampling distribution is the standard error. So this slide gives you the formulae used to construct standard error. So just to recap, you know what standard error is. It's the standard deviation of the sampling distribution, and it indicates how different the population mean is likely to be from a sample mean. So as you can see, to calculate the standard error, the population standard deviation and the sample size is used. So if you know the population standard deviation, it's best that you use it because it gives a more precise value for the standard error. But if you don't know the standard deviation of the population, then you will have to substitute the sample standard deviation instead, and then it gives a gives an estimate, a less precise estimate for the standard error. So I'm sure in the previous lecture you have covered the standard normal distribution, calculation of Z scores, and referring the Z tables to find the corresponding p-value. However, I thought I'll revisit some of these areas just to recap. And the standard normal distribution is also known as the Z distribution, and it's a special normal distribution where the mean is 0 and the standard deviation is 1. So it's a probability distribution, and therefore the area under the curve is 1, or if you give it as a percentage, it would be 100%. Then the area between 1 is 68%, and then the area between 2 STs is 95%, and the area between 3 STs covers 99%, actually more than 99% of the total area. So any normal distribution can be standardized in this way by converting its values into Z scores. So the respective Z scores tell you how many standard deviations from the mean each value lies. So in that case, every Z score has an associated p-value, a corresponding p-value that tells you the probability of all values below or above that Z score. Okay, so that is how when you calculate the Z score by referring to the Z tables, you can find the probability, that is the p-value of all values below or above the respective Z score. So this slide gives you some information about the point estimate and the interval estimate. So what is a point estimate? It is the estimated value of a population parameter. You know, you use samples to calculate the mean, mode, median, standard deviation, whatever. So all those are point estimates. Then point estimation is the use of this value of the sample statistic as the estimate of the value of a population parameter. So the point estimates are rarely the same as the population parameter due to sampling error that we have discussed already. But sample statistics serves as the best estimate for a population parameter. So therefore, it is important to know the point estimate. So, what is the interval estimates then? They are also known as confidence intervals. They are constructed by using the point estimate and the standard error. Now, if someone asks you what the confidence interval is, you have to say that it's a range of numbers. It's important to note these words. It's a range of numbers inferred from the sample, but has a certain probability or chance of including the population parameter. It has a certain probability or chance of including the population parameter. Then there are some more definitions here. What is a confidence limit? You know, now in a range there are two endpoints, and these two endpoints are known as confidence limits. So the lower limit is the smaller number and the upper limit is the larger number. Then moving to the level of confidence. What is the level of confidence? It's the probability that a confidence interval constructed from a random sample will include the population parameter. So it's a probability that a confidence interval constructed from a random sample will include the population parameter. So this slide gives you the formulae for construction of confidence interval. And a confidence interval, is the mean of your estimate plus and minus the variation in that estimate. So if you have the population standard deviation, you can use it as we stated earlier. But however, in real life, unless you carry out a census, you don't have the population data. So therefore, you can always use your sample means or the sample statistic, whatever it is, calculate your confidence interval. Right. So moving on. So let's look at an example to understand the construction of confidence interval. Let's say the mean diastolic blood pressure of a sample of 72 patients was found to be 88 mercury millimeters and the standard deviation 4.5 mercury millimeters. Therefore, the confidence limits will fall 1.96 standard deviations above and 1.96 standard deviations below the mean. So, here I have given the calculation. You need to substitute the figures, these values, to the formula I gave you in the previous slide. And the result is that the lower limit is 79.2 mercury millimeters and the upper level is 96.8 mercury millimeters. So the 95 limits are often referred to as the reference range. For many biological variables, they define what is regarded as the normal range. Anything outside the range is regarded as abnormal. If a series of such samples are drawn from the population and the mean of each calculated, then the 95% of the means would be expected to fall within the range of 2 standard errors above and 2 below the mean of these means. So in that case, 95 confidence interval for the population parameter is the mean plus or minus 1.96 into standard error. So then the lower limit is 86.96 mercury millimeters and upper limit is 89.04 mercury millimeters. So what does this mean? There is only a 5% chance that the range 86.96 to 89.04 mercury millimeters excludes the mean of the population. So in other words, you can also say that you are 95% confident that the range 86.96 to 89.04 will encompass the true population mean. So some facts about the confidence interval. Well, 95% confidence interval will 95% of the time will capture the population parameter. The 99 confidence interval is wider than the 95% confidence interval and therefore is less precise. When a range is wider, the precision drops. Then when the sample size is increased, the confidence interval is narrowed and therefore it becomes more precise. These are some important facts that you have to keep in mind. Okay. So moving on to hypothesis testing. Hypothesis testing is used to assess the plausibility of a hypothesis by using sample data. That we have mentioned earlier on this lecture, so you already know that. Then what is a hypothesis? It is a predictive statement that relates an independent variable to some dependent variable, or independent variables to some dependent variable, and is capable of being tested by scientific methods. Now you need to know what null hypothesis is and what an alternative hypothesis is. Null hypothesis is denoted by H naught and is known as the conjecture. Assumes that any kind of difference between the chosen characteristics that you see in a set of data is purely due to chance. For example, if the expected earnings in a gambling game are truly equal to 0, then any difference between the average earnings in the data is 0 due to chance. So what is an alternative hypothesis? It is a statement where the population parameter takes some value other than the value stated in the null hypothesis. Moving on. This slide gives the steps you need to follow when testing a hypothesis. So after developing your initial research hypothesis, that is the prediction that you want to investigate, so it is important to restate it as a null hypothesis and an alternate hypothesis. So that the idea is so that you can test it mathematically. Then you know that alternate hypothesis is usually your initial hypothesis that predicts the relationship between the variables you are interested in. So then the null hypothesis is a prediction of no relationship between the variables you are interested in. So then the next step is to formulate an analysis plan. So you need to state a significance level, maybe it's 1%, 5% or 10%. But usually for biological variables, we take 5% as the significance level. Then decide a test statistic. Maybe you can run a Z test, a T test or an F test depending on the study. So how you choose this would be discussed later on this lecture. Then the third step is analyze the sample and calculate the value of test statistics and look up the p-value at given significance level from the table. Then the last step is compare the p-value with calculated value. Say the p-value is greater than the calculated value, then you do not reject the null hypothesis. Then if the p-value is less than calculated value, then you reject the null hypothesis. So for an example, let's say you want to test whether there is a relationship between gender and height, right? So based on your knowledge of human physiology, you formulate a hypothesis that men are on average taller than women. So to test this hypothesis, you need to restate the hypothesis as the null hypothesis and the alternate hypothesis. So in this case, the null hypothesis would be men are on average not taller than women. Then the alternate hypothesis would be men are on average taller than women. So then you need to formulate your analysis plan and you decide that you are taking 5% significant level and you decide on Z test, right? Say your sample is about 200 and you choose Z test. So then you analyze it and you have a calculated value, and you look up the p-value, the corresponding p-value for that calculated Z score, Z statistic, and you get 0.002. Let's say, right, arbitrarily we are just saying for as an example. Then your cutoff point, which you have fixed earlier on, is 0.05. So then you know that your the p-value is less than the calculated value. Therefore, you reject the null hypothesis of no difference, and you say that there is a difference between the height of the males and females in your sample, and therefore you ultimately conclude that there is a difference in heights between the genders. So let's try to understand type 1 and type 2 errors. So making a statistical decision always involves uncertainties. So the risk of making these errors are unavoidable in hypothesis testing. So if you reject the null hypothesis when actually it is true, you are committing a type 1 error. On the other hand, if you do not reject the null hypothesis when it is false, you are committing a type 2 error. Now, when considering the type 1 error, the risk of making a type 1 error is the significance level or the alpha level you have chosen. So that's the value that you set at the beginning of your study to assess the statistical probability of obtaining your results. So in a null hypothesis distribution curve, the tail end represents alpha. So it is also called a critical area, the critical region in statistics. Okay. So if you fail to, as we already mentioned, if you fail to reject the null hypothesis when it is false, then you are committing a type 2 error. So type 2 error means failing to conclude there was an effect when there actually was. So in reality, your study may not have had enough statistical power to detect an effect of a certain size. So what is power? Power is the extent to which a test can correctly detect a real effect when there is one. So usually a power level of 80% or higher is considered acceptable. So the risk of a type 2 error is inversely related to the statistical power of a study. The higher the statistical power, the lower the probability of making a type 2 error. So usually we denote the type 2 error rate by beta. So the remaining area under the curve will be then 1 minus beta, and that represents the statistical power. Okay, let's talk a little bit more about the significance level. Significance level denoted by alpha is a value that the researcher sets in advance as the threshold for statistical significance that you already know. So it is the maximum risk of making a false positive conclusion, that is a type 1 error, which we discussed in the previous slide. So that is the maximum risk of making a false positive conclusion that the researcher is willing to accept. So usually the significance level is set at 0.05 or 5%. So if the p-value is higher than the significance level, the null hypothesis is not refuted and the results are reported as not statistically significant. But if the p-value is lower than the significance level, the results are interpreted as statistically significant. You refute the null hypothesis and report the results as statistically significant. So, what is a test statistic? It's a calculated statistical value using a statistical test. So, these are the appropriate statistical tests for a given test statistic. So, I have given the corresponding null hypothesis and the alternative hypothesis too. So, you are not supposed to learn the F value much as an undergraduate, but I have put it for completeness sake. The chi value is for categorical data, and Z and T value are used for means, to see the difference between two means. So F value is for more than two means. So moving on, the test statistics explained further. It describes how closely the distribution of your data matches the distribution predicted under the null hypothesis of the statistical test used. So the agreement between the calculated test statistic and the predicted value is described by the p-value. The smaller the p-value, the less likely the test statistic is to have occurred under the null hypothesis of the statistical test. So, because the test statistic is generated from observed data, the smaller the p-value, the less likely it is that the observed data could have occurred if the null hypothesis was true. So, you don't need to by heart all these things, just get the concept, right? So, if you go through the steps in hypothesis testing, you will again realize what I'm trying to convey here to you. The p-value is a number calculated from a statistical test that describes how likely it is to find a particular set of observations if the null hypothesis were true. So, the p-values are used in hypothesis testing to help decide whether to reject the null hypothesis. The smaller the p-value, the more likely you are to reject the null hypothesis. The most common threshold is p lesser than 0.05, where a test statistic as extreme as one calculated by the test is expected to be found only 5% of the time. So a little bit about the statistical power and effect size. A statistical power is the likelihood of detecting the effect when there actually is one. So a high power in a study indicates a large chance of a test detecting a true effect. So the power is mainly influenced by the sample size, effect size, and significance level. So a power analysis can be used to determine the necessary sample size for a study. So then what is an effect size? It's a number that measures the strength of the relationship between two variables. So how is this effect size calculated is for paired quantitative data, correlation of determination is used. For relationship difference between means, cohens D, which you don't have to know at all. And for relationship between categorical variables, some of this you may learn later on. The risk ratio, that is relative risk, the risk difference, and odds ratios can be used.